Dear cadets, Assalamu alaikum. Welcome you all at my online class. This is Maqsudur Rahman, lecturer in chemistry, Borishal Cadet College, Borishal. Considering prevailing situation, Borishal Cadet College is providing necessary academic guidelines and short lecture on specific link periodically. It is very necessary to keep yourself inside home along with your family members for avoiding the running pandemic COVID-19. You can see a building of Mexican University designed with a periodic table. So I think you can guess the today's topic. Yes, today I discuss on chapter 3, periodic properties of elements and chemical bond. And this is first session for class 11. At the end of this lesson, you will be able to define SPD and A block elements. You can explain the formation of color compound by D block elements. You can analyze the reason behind the magnetic properties of D block elements, and also you can explain the inner transition elements. So today's important topics are block elements, transition elements, magnetism, and inner transition elements. Now, position of block elements in periodic table. You can see S, D, P, and F orbitals in the periodic table. Now, S block elements. The S block elements of the periodic table are those in which the last electron enters into the outermost S orbital. Here is an example. You know the atomic number of sodium is 11. So its electronic configuration is 1s2, 2s2, 2p6 and 3s1. So as its last electron enters into S orbital, this is known as S block elements. The general electronic configuration of S block elements is noble gas and NS1. This is for alkali metals, and noble gas and NS2 for alkaline earth metals. Another example, magnesium, its atomic number is 12. So its electronic configuration is 1s2, 2s2, 2p6 and 3s2. This is example of alkaline earth metals. As its last electron enters into S orbital, this is known as S block elements. From these two examples, we can see that S orbital can accommodate 2 electrons, 1 and 2. So when it accommodates 1 electron, this is for alkali metals, and when it accommodates 2 electrons, this is for alkaline earth metal. In picture, you can see this is group 1A, this is alkali metals, and this is alkaline earth metals. Now, the elements of group 1 include lithium, sodium, potassium, rubidium, cesium, and francium. These metals are known as alkali metals because the hydroxide of these compounds are alkaline in nature. As these hydroxide of these compounds are alkaline in nature, these are called alkali metals. And in case of group 2 includes beryllium, magnesium, calcium, strontium, barium, and radium. These metals are known as alkaline earth metal. Why these substances are known as alkaline earth metal? Because oxide and hydroxide of these metals are alkaline in nature, and the metal oxides of these metals are found in earth crust. As these oxide and hydroxide of these metals are alkaline in nature and metal oxide are found in earth crust, these are known as alkaline earth metals. Now, P block elements. P block elements are the elements in which the last electron enters into the outermost p orbital. Here is an example, nitrogen. Its atomic number is 7. If we write down the electronic configuration of nitrogen, that is 1s2, 2s2 and 2p3. As its last electron enters into p orbital, this is called p block element. The general electronic configuration of p block elements are ns2, np, 1 to 6. Here p orbital can accommodate maximum 6 electrons. Another example, carbon 6, its atomic number is 6. So its electronic configuration is 1s2, 2s2 and 2p2. As its last electron enters into p orbital, this is called p block elements. These p block elements include 6 groups. That is group 13 to group 18. Group 13 is known as boron family. This is known as boron family. It starts with boron. Group 14 is known as carbon family. It starts with carbon. And group 15 is known as nitrogens family. It starts with nitrogen. Group 16 is known as chalcogen family. It starts with oxygen. And group 17 is known as halogens family. It starts with fluorine. And group 18, it is called noble gas family, and it starts with neon. Helium is not p block element. It is an example of s block elements. So now metals, these are the metals, non-metals. These substances are non-metals, and these are metalloids. All these three types of elements are present in p block elements, and the heaviest element in p block elements are metals, and non-metallic character of elements decreases towards down the group. Now d block elements, the elements in which the last electron enters into the d orbital of the penultimate shell, that means inner shell of the outermost shell, is known as penultimate shell. So the elements in which the last electron enters into d orbital is called d block elements. Here is an example: scandium. Its atomic number is 21. So its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 1 and 4s2. As its last electron enters into penultimate shell, that means inner shell of the outermost shell, this is called d block elements. Here you can see the position of d block elements. You can see from group 3 to group 12, all these elements are known as d block elements. Now d block elements are located in between s block and p block elements. That means in the middle part of the periodic table we have d block elements, and it starts from group period 4 to period 7th, and group 3 to group 12. All these elements are d block elements. Now there are 4 transition series, that is 4d, 3d, 4d, 5d and 6d series. What is 3d series? The 3d series contain the elements from scandium to zinc, and it belongs to 4th period. And group 4d series contains the elements from yttrium to cadmium, and it belongs to 5th period. The 5d series begins with lanthanum and contains the element from hafnium to mercury, and this belonging to the 6th period. And last one is 6d series. It begins with actinium and contains elements of rutherfordium to copernicium, belonging to 7th period. Now electronic configuration of d block elements. The first one is 3d series. 3d series or first transition series, it starts from scandium to zinc, belonging to the 4th period. Its electronic configuration are like this. Here you can see there are 2 anomalies or 2 exceptional electronic configuration, that is chromium and copper. In case of chromium and copper, there are 2 exceptional electronic configuration. Now I going to discuss about this exceptional electronic configuration. First one is in case of chromium. Why does chromium show abnormal or exceptional electronic configuration? You know that atomic number of chromium is 24. So its electronic configuration, expected electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d4 and 4s2. But its actual electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s1. Why? Because the energy difference between 3d and 4s orbital is very low, and electron-electron repulsion results in the transfer of one orbital from s orbital to d orbital. as the d orbitals being degenerate, when one electron comes out from s orbital into d orbital becomes half filled. And when d orbitals become half filled or full filled, it gets more stability. As in this case, in case of chromium, d orbital gets half filled, that means 3d5, it gets more stability. That's why its it show exceptional electronic configuration. Another one is that is copper. Copper also show abnormal or exceptional electronic configuration. Why? You know that its atomic number is 21. Its expected electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, and 4s2. But its actual electronic configuration is 3d10 and 4s1. Why this? Answer is same. The energy difference between 3d and 4s is very low. So electron-electron repulsion occur between in s orbital, and one electron from s orbital travels from s to d orbital. In that case, d orbital becomes full filled. Maximum electron present in d orbital, that means 3d10. When d orbital becomes fulfilled, it gets more stability. That's why copper show exceptional electronic configuration. Now, the electronic configuration of series, that means 3D, 4D, 5D, and 6D series. In case of 3D series, we write it as argon 3D 1 to 10 and 4s 1 to 2. For example, scandium, its atomic number is 21, so its electronic configuration is argon 3d1 and 4s2. In case of 4D series, that belongs to period 5, it starts with krypton 4d1 to 10, 5s2. Here is an example. Yttrium, its atomic number is 39, so its electronic configuration is like this: krypton 3d1 and 5s2. In case of 5D series, that belonging to period 6, it starts with xenon 5d 1 to 10, 6s 1 to 2, and its example is lanthanum. Its atomic number is 57 and its electronic configuration is xenon 5d1 and 6d2. And last one is 6D series. It belonging to period 7 and its electronic configuration is radon 6d1 to 10 and 7s 1 to 2. And here is an example, actinium. Its atomic number is 89, so its electronic configuration is radon 6d1 7s 2. Why are d block elements are called transition elements? Because the position of d block elements are in between s block and p block elements. That's why these d block elements show or exhibit transitional behavior between s and p block elements. And you know that s block elements are highly electropositive elements, or these elements are metallic in nature and form ionic compounds. And p block elements, these are electronegative elements and try to form covalent compounds. As d block elements are present in between s block and p block elements, these d block elements show characteristics of s block and also p block elements. For example, potassium ferrocyanide, here central atom is iron. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. As its electron enters into 3d orbital, this is d block elements, and when it forms compound, it lost 2 electron and form Fe2+. As it forms Fe2+, it has 3d6 electron. That means in d orbital there are 6 electrons. So this is transition element. What are transition elements? The elements in which d orbitals are half filled, d orbitals are partially filled, not full filled. These are transition elements. So in case of potassium ferrocyanide, it lost 2 electron. That means it forms ion. So it behaves like s orbital, s block elements. And when it forms compound with cyanide, cyanide can coordinate with iron. So there is a characteristics of p block elements. So we can say that d block elements or transition elements show characteristics in between s block and p block elements. That's why these substances are known as transition elements. All d block elements are not transition elements. Why? In previously we know that d block elements are those in which the last electron enters into d orbital, and transition elements are those elements which have incompletely filled, that means partially filled d orbitals in their elementary state or in their oxidation state. Here is an example. Iron, its atomic number is 26, its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 and 4s2. As its last electron enters into penultimate shell, that means 3d6, it is called d block elements. And as its d orbital is partially filled, not incomplete, is not complete, that's why it is called transition elements. And when it forms ion, you can see there is also incomplete d orbital. So this is called transition and d block elements. So why d blocks are not transition? Because when d block elements that contain full filled d orbitals, or if there is no electrons in the d orbital, that d elements are known as d block, not transition. For example, zinc, its atomic number is 30. If I write its electronic configuration like this, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s2, you can see this d orbital is fulfilled. As this d orbital is fulfilled, this is only d block, not transition. And in its oxidation state, that means when it forms ion, you can also see that d orbital is fulfilled. That's why it is d block, not transition element. Another example for your better understanding, that is scandium. Its atomic number is 21. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1 and 4s2. As its last electron enters into penultimate shell, that means 3d1, it is d block elements. And its stable ion, that means scandium 3+. In case of scandium 3+, there is no electron in d orbitals. As there is no electron in d orbital, this is d block, not transition. So we can say that a d block elements become transition when it have partially filled d orbitals, not fulfilled or zero electron in d orbitals. Now, most of the transition metal compounds are colored. Why? In a free transition metal ion, the 5 d orbitals are degenerate. What is degenerate? That means all d orbitals have same energy. But when transition metal form compounds, these 5d orbitals splits into two groups according to crystal field theory. First one is lower energy level. This contains 3 orbitals, dxy, dyz and dzx. And higher energy orbital contain 2 orbitals, that is dx square minus y square and dz square. And it is noticed that the difference between the two energy level is very small. So as the transition metal ion have unpaired d electrons, which on absorbing visual light can jump from one d orbital to another d orbital. That means dd transition can occur. So when light falls, certain visible wavelengths are absorbed, and the color observed is different from the color absorbed. The color observed is the color transmitted and is complementary to the color absorbed. What is complementary color? Here you can see, if light fall on a substance with a wavelength of red color, we can see the color of the substance is green, because green is the complementary to red color. So if a light fall on a substance that contain wavelength of violet, we can see the light of yellow color, because yellow is the complementary color of violet. So hence, that's why transition metal compounds are remarkably colored substance due to D to D transition. And most of the transition metal compounds are colored. If I summarize this, you can see in degenerate state, these d orbitals are, all d orbitals have same energy, but in case of formation of compound, these d orbitals is split into two groups. Lower energy, there is 3 orbitals, and in higher energy level there are 2 orbitals. And when light fall on it, here is an example. If greenish yellow light falls on this compound, we get reddish color, because reddish color is the complementary of greenish yellow light. So now here is another question: why are some of the transition metal ions are colorless? You know that transition metal ions exhibit color due to the presence of unpaired electrons in d orbitals. That means when d orbitals have unpaired electrons, there will be possible for d to d transition. But if the metal ion which do not have unpaired electron, that means if there is no electron, that means d is 0, or the elements which have completely filled d orbitals, that means if the elements contain d10, they do not absorb radiation in visible region, because d to d transition are not possible. Hence they are colorless. Example, zinc 2 plus, its atomic number is 30. If we write down its atomic number, we can see that in its outermost shell there are 3d10. That means d orbital is fulfilled. As this d orbital is fulfilled, there is no possible of d to d transition. That's why this substance do not absorb radiation in visible region and cannot emit light of visible region. So these substances are colorless. More examples is canadium 3 plus. It has no electron in d orbital. Copper plus, silver plus, cadmium 2 plus. These 3 elements has fulfilled d orbital fulfilled. That's why there is no possible of dd transition. That's why they doesn't form any color compound. Now, magnetic property of d block elements. Magnetism is a property is due to the presence of unpaired electrons. When in elements there are pair electrons, they show diamagnetic property, and when in elements has unpaired electron, it show paramagnetic properties. So in case of transition elements, most of the transition elements have unpaired electron. Most of the transition elements have unpaired electron in d orbitals. That's why they can show paramagnetic properties. And paramagnetic characteristics increases with increase the number of unpaired electron. So if a substance have maximum number of unpaired electron, this is known as ferromagnetic. Here is a question: why are zinc metal and zinc 2 plus ion are diamagnetic in nature? You can see, you know that the atomic number of zinc is 30. Its electronic configuration of zinc is argon 3d10 and 4s2. As its d orbital is fulfilled, that means all electrons are paired. So this is diamagnetic in nature. And in case of zinc 2 plus, you can also see that d orbitals is fulfilled. As this d orbital is fulfilled and paired, hence they are diamagnetic in nature. But why in Fe3 plus ions are ferromagnetic? You can see the electronic configuration of Fe3 plus is argon 3d5 and 4s0. That means in d orbital, all 5 electrons are unpaired. All 5 electrons in d orbital are unpaired. As it has 5 unpaired electrons, it is ferromagnetic in nature. So now, F block elements. The elements in which the last electron enters into N2 minus F orbital, that means F orbital of the atoms, are called F block elements. In these elements, the last electron enters into the pre-penultimate shell. What is pre-penultimate shell? This is the inner shell of the penultimate shell. What is penultimate? This is outermost shell of the outermost shell. This is outermost shell, this is penultimate shell, and this is pre-penultimate shell. As the electrons enters into the f orbitals that is present in the pre-penultimate shell of the outermost shell, this is known as inner transition elements. Here you can see the inner transition elements, that is lanthanide series and actinide series. These are known as F block elements. Now, why F block elements are called inner transition elements? The last electron in the F block elements enter into f orbitals, and this f orbitals is inner to the pre-penultimate energy level, and they form transition series within D block elements. That's why these F block elements are called inner transition elements. You can see the figure. There are two series of inner transition elements or F block elements. One is lanthanide series and another one is actinide series. So what are lanthanide series? The series involving the filling of 4 f orbitals following lanthanum is called lanthanide series. These elements present in this series are called lanthanides because the properties of these elements are nearly same with the properties of lanthanum, and it starts from cerium to lutetium. These 14 elements are called lanthanide series. Lanthanum is not A block elements, this is D block elements. Now, what are actinide series? The series of elements from thorium to lawrencium in which 5 f orbitals are progressively filled are called actinides. Except actinides, these 14 elements are called actinide series. It starts with thorium and ends with lawrencium. These elements are called actinide because the physical and chemical properties of all these substances are nearly similar with actinum. That's why this series of elements are known as actinide series. So if I summarize D and F orbital electron elements, D block elements are known as transition elements. It starts with group 3 to group 12, and F block elements are known as inner transition elements. So in case of D block elements, first one is 3D series. It starts with scandium to zinc, and 4D series, it starts with yttrium to cadmium. 5D series, it starts with lawrencium, hafnium, and hafnium to mercury. And last one is 6D series. This starts with actinium and contains rutherfordium to copernicium. And in case of inner transition elements, there are two series. One is lanthanide, another one is actinide series. In case of lanthanide, it is known as first inner transition series elements, and it starts from cerium to lutetium. And in case of actinide series, it is known as second inner transition elements, and it starts from thorium to lawrencium. So today we learned about the definition of S, P, D, and F block elements, the formation of colored compound by D block elements, and the magnetism property of D block elements. So if you have any question, please write it in comment box. And here is an homework for you. First question, what are S block elements? Second one is, why does copper show abnormal electronic configuration? Third one, explain why is Fe3 plus is more stable than Fe2 plus. And last one, scandium 3 plus is colorless while titanium 3 plus colored. Analyze it. Here atomic number of scandium is 21 and titanium is 22. So thank you very much for your participation. I want to say you again that you must stay at home, make your family members conscious about novel coronavirus COVID-19. Stay home and continue your study and make the best use of your time. Thank you. Thank you very much.